Okay, I'm gonna open up chapter 2. I want you to say hi, please, to make sure that you are here with me. May I get the hi? Okay, thank you very much. All right, very good. And we are gonna. So I'm gonna share the screen. Okay. Okay. So in chapter 2, we are going to be talking about limits and continuity. All right. So we have a couple of sections to cover. The first section is about rates of change and tangent lines to curves. Okay. So we are going to start. I think there's a question. Let me check. Oh, yeah. No questions. Okay. Okay. So I want to start with the daily life used formula, which is actually this is average speed. So we are either moving, traveling, walking, driving, etc. There's a motion going on, and speed comes with it. And we want to calculate the average speed. So how would you do that? It is simple. So you're gonna compute the distance traveled, and you're gonna divide this by how many minutes you traveled, and you get the average speed, right? Average speed of your cells or of the car, of the object that's traveling, that's moving. Okay. So here, f of t is going to be the distance. It's the distance function. Okay, it's gonna show f of t is gonna show the distance traveled at time t. For example, f of 0 is 0 because at time t is equal to 0, you don't move anywhere. Okay, but f of 5, maybe it is 10 kilometers. It's or 10 meters. It just shows how far you traveled. Okay, you moved, or the object moved. Okay. So therefore, here's the definition. Average speed over the time t1, t2 is the distance traveled on that time interval over the time that's covered, so elapsed. Okay. So f of t2 minus f of t1 over t2 minus t1. So this is a very easy formula to remember, to understand. Next, what do we want to do? We want to find the average speed over a couple of intervals, but these intervals are going to be one inside another. Okay. So we are going to have interval from t0 to t0 plus h. The interval length is h. Okay. And then, but our goal is to make this interval smaller and smaller. What does it mean? We are going to have, let's see what I wrote here. Maybe I have some pictures here. Okay, so I'm talking about this thing that is that's at time t is equal to 0. Let's say the object is here. Let's put an object here. Maybe I can put an x here, or capital X. Let's make it larger. Okay, it should be large. Why doesn't it? Okay. Okay, X. Okay, good. Or maybe, what should I say? I should use a Q or something. Okay, the object Q is here, and then after Q is not good either. What should I put? Or maybe I should say A to B. Okay, let's say this is a distance from A to B, and the object is traveling from A to B. At time t is equal to t naught, it is at ta, and at time t is equal to t0 plus h, it is at b. Okay, we can see it like that too. Okay, this is the picture you can say, maybe I should do it like this. Okay, to be able to have a better picture. Okay, I think this is a better picture. Okay, at time t is equal to 0, you're at A. At time t is equal to t naught plus h, you're at B. And you're traveling. And we are interested in finding the average speed in smaller and smaller intervals. But these intervals are all going to be close to, so we are going to change this h, make it smaller and smaller. For example, h is equal to 5, h is equal to 2, h is equal to 1, h is equal to 0.05, h is equal to 0.005, h is equal to 0.0000001. If you do that, you are having smaller and smaller intervals close to A. Okay, so I'm interested in finding the average velocity as I get close to A. Why am I doing this? Because I'm interested in finding the speed at t is equal to t naught. So it's whenever time t is equal to t naught, I'm interested in instantaneous speed, instantaneous velocity, the instant velocity. I need to find it. Okay, so that's why I'm just calculating the average velocities, and as I get close to the point A, I'm gonna get a closer value to the instantaneous velocity at A. These tables are showing that. By the way, my distance, I wrote it here. My distance function in this question is this. This is the distance function. Okay, let me write example here. Okay, f of t is given as a distance function, and it's given, and h represents a time interval. We have the t0 time is equal to 1, and we are also given time is equal to 2 as well. It's in another subject. So the question is calculate the or form just a sec, form a table of average velocities, average speeds, as h gets very small, very small. Okay, this is the same as getting numbers close to the instantaneous velocity, instantaneous speed at time t is equal to t naught. Okay, so we want the exact speed. We want to find the instant speed at t is equal to t naught. That's the goal. In order to get to it, we built such a table containing the numbers of average speed. Okay. So each time you're going to have, for example, next you're going to have another. Okay, let's say. Okay, I'm not going to go into this anymore. Okay, I don't want to dramatize this one. I'm going to just show you the table here. So the table says, for example, h is 1 first and then 0.1, and our interval is getting smaller and smaller, 0.01, 0.001, and right? And then the average speed over the interval of length h starting at t0 is equal to 1. At first it's 48, but it drops down to 32.0016. So this is showing that actually the instantaneous speed at time t is equal to 1 is close to 32. Okay, we can build another table to find the instantaneous speed at time t is equal to 2. Let's say after 2 hours, what is the speed of what's the speed of this object? We cannot find the exact value, but we can find a good guess. a good guess by building this table. So as you get close to that amount, like as h gets smaller and smaller, the values of the average speed drops down to 64.0016. So this is going to tell you that at time t is equal to 2, at time after 2 hours, at time 2, okay, from the start we can say maybe, it's going to be 64, close to 64 miles per hour if it is in terms of miles, okay? So I just write them down like it here. Our goal is to find the instantaneous instant speed at time t is equal to t naught is equal to 1. It is not approximate, actually. You won't be able to find exact yet. But in our future goal is to find exact value, approximate instantaneous, right? Approximately, you can find it. You cannot find it exactly. This tool is not good enough for it, okay? But in this, in chapter 2, we will be able to find the answer to that. We will be able to find exact instantaneous speed there, okay? So what we are going to do, you'll calculate average speed in an interval h, where h gets smaller and smaller so that it's almost zero value. So from the table, we get that the instantaneous speed, instant speed at time t naught is equal to 1 is close to 32 miles per hour. Let's say the unit is in terms of miles and hours, okay? How about find the approximately, of course, find approximately. Maybe I should put this in approximately, okay, before it. Find approximately, okay, it should be before it. Otherwise, it doesn't make sense. Okay? Find approximately the instantaneous, namely instant speed at time t naught is equal to 2. Again, we cannot find it exactly yet, but we can find a close value, and we build this table, and the table says, okay, from the table we get that instantaneous speed at time t is equal to 2 is close to 64 miles per hour, okay? We just use the formula that we introduced here. So this is the formula we introduced. That's the only thing we used. Okay. Okay. So finding the average speed and then using this average speeds and trying to get approximate value to the instantaneous velocity is what we covered so far. Now, this was from daily life. So we use speed in our daily lives, right? So can we generalize this fact? Yes, we can. In general, actually, this type of things we need not only in finding the instantaneous speed, but you can find instantaneous of something else. Okay, so therefore we should generalize this fact. And just a sec, I'm sorry. Okay, sorry about that. Let me turn this down. I did that, but for some reason it just keeps doing that. Okay, anyways. So average rate of change is the general name to it. Okay, average rate of change of a function with respect to the variable x over an interval. So the formula, see, it is the same. So we have a function f that represents something. In the previous case, it was representing the distance. But this f could represent anything that we are interested in from daily life, okay, or from an abstract theory. And then we just look at this differences in the image over differences in the x values, and this ratio, which is delta y over delta x indeed, is going to give us the average rate of change. Okay, instead of x1 and x2, we can use x1 plus h as if the interval has length h here. Okay, be careful here, h is never ever 0 here. Okay, so this is average rate of change is an important thing to look at, because it's going to give us the instantaneous something to us, like instantaneous speed, instantaneous this and that. Okay. Okay, so here is pictorially you can see. So this is our f that we are taught, and we have delta y, delta x. We just said that delta y is f of x2 minus f of x1. Delta x is x2 minus x1. And if you take the ratio of the two, delta y over delta x, actually it's a slope of a line. And this line is actually a secant line, okay? Secant line. So let's remember what a secant line is, okay? Secant line is a line that's combining 2 points on the graph, okay? That's the definition. Let me put it like this. Secant line can be formed, okay, or is a line, okay, obtained by connecting. Let's write it like that. Is a line, okay, obtained by is a line obtained by connecting 2 points on the graph of f. Okay, tangent line, on the other hand, it's a line intersecting the graph of f at one point. That's the definition of the tangent line. Okay, we have some notes here. We just said, actually, okay, the average rate of f, okay, average rate of change of f is the slope of the secant line. It's delta y over delta x, which is the same as the slope of the secant line. Secant lines are as important as tangent lines, so they are very important. Actually, that's secant lines. We use them to get the exact value of the. Okay, maybe I should write that too. Indeed, we use. Okay, or people in the ancient times, they used, okay, secant lines, okay, maybe people in ancient times, people or mathematicians in ancient times, maybe we should say mathematicians in ancient times, ancient is too ancient, in all times, okay, ancient in all times, mathematicians in all times used secant lines to find the slope of the tangent line. So if you know the slope, secant lines, then you can easily find the slope of the tangent lines. But you won't be able to find the tangent lines in any other way. You need the secant lines. Okay, that's where it started. Later on, they just built the theory. Okay, they built the differentiation, and then they said that if you take the derivative and equate at a point, you get the slope. Okay, but all these differentiation, etc., came from this secant lines, these average rates, etc. Okay, this is the background of all these differentiation tool. Okay, all right, so a secant to the graph y is f of x, you see here the black line, its slope is delta y over delta x, we said, and the average rate of change of f over the interval x1, x2. So from here you should remember average rate of change of f over an interval is the same as the slope of the secant line. You should keep this in mind. Okay, let's see a tangent line. Consider a circle. A circle has a radius r. We don't care how much, and it has an origin. And then we have a line that's intersecting the circle, the graph of the circle at one point. Okay, this is actually the tangent line to the circle. Okay, tangent line of the circle. Okay, so L, the line L, the tangent line L, is tangent to the circle at the point P if it passes through P perpendicular to the radius OP. So it has to be perpendicular. That's the definition of the tangent line to the circle. Okay, of the circle. Okay, now, and then we had, I told you secant lines, and I told you that secant lines are useful to get to the tangent line, and this picture shows it. So we have secant lines here. Okay, we have secant lines here. And these secant lines, do you see that they are getting closer and closer to tangent line? Yes. And can you observe that the slope of the secant lines are getting closer to the slope of the tangent line because they are almost parallel here. Like if you consider this blue one and the red one, they're almost parallel to each other. So, I mean, that would mean that they are very close to each other, which would mean that their slopes are very close to each other. So actually, the slopes of the secant line approaches to the slope of the tangent line. Okay? So in other words, delta y over delta x's are getting close to the slope of the tangent line. Actually, this is very reasonable because differentiation comes from it. Delta y over delta x actually in the limit is the derivative of the curve, okay, at that point P, okay, and which is going to give you the slope of the tangent line, okay? So these are all related to each other. And you can approach, you can form these secant lines by moving this Q point on the graph towards left, and you can form all these secant lines, but you can do this from the left as well. You can put a Q on the left of P, and then you can start building your secant lines, and then here's another one, and these ones are getting closer and closer to the red line, which is the tangent line. So here Q is approaching to P. Look at that. Q is approaching to P from either side. It's approaching from the right, and Q is approaching from the left. Okay? So let's see what it says. The tangent line to the curve at P is the line through P whose slope is the limit of the secant line slopes as Q goes to P from either side. Okay? So, yeah. So let's see what I wrote here. If you have any questions, stop me, okay? Say I only know the slopes of the secant lines, say I know the slope values of the secant lines, then just take the limit of those slope values and you get the number that you get is the slope of the tangent line, okay? Observe that slopes of the secant lines are getting closer to the slope of the tangent line, okay? All right, that's the story of it. That's where actually differentiation comes from. Okay, differentiation theory comes from it. Okay, do you have any questions or am I going too fast? Because maybe it's not very interactive and maybe, is it difficult or are you doing fine? Are you doing well?
Sure, it's difficult, but we are trying to solve that.
Are you with me?
Yes.
Yes, teacher, we are.
We are with you, but it is difficult.
Teacher?
Hello. I think my internet connection stopped. That's why I tried to log in, couldn't. So I'm back in here. You can hear me, right? So I'm connected.
Yes.
Great. Let's see whether it's recording. Yeah, it's still recording. That's good. Okay. So let's move on. Actually, where we left off is a good place to stop, actually, if you want. We have 8 minutes? No, we still have some time, I guess. Okay, let me talk to you about this. And
can you share your screen, teacher?
Yes, you're right. I will do that. Okay. Okay, so this is the picture that I want to talk to you. Actually, this is an example of what we just said. Okay, so I want you to observe this picture. So we have this blue one is the y is equal to x squared. And we have the point Q here. And we have the point P here. So this point Q is moving towards P, you can consider. Because each time this Q is moving towards P, we have different secant lines. And these secant lines, of course, they have slopes. Each time there's a different slope, right? Because this line is going to be like getting closer to this tangent line, and it's going to be a different slope. Okay, we just collect them, we just look at them, we just put them in a table, and then as Q gets close to the P, we want to see where they approach to, which number they get close to. Okay, our function is y is equal to x squared. What is the secant slope? It is delta y over delta x. What is delta y here? Delta y is f of, okay, we have the x, we have the 2 and 2 plus h. So the interval is h at the beginning. Okay, and this h is going to, we are going to make it smaller and smaller. When you make this h smaller and smaller, that would mean your Q is getting close to P, right? If you choose h smaller enough that you have this point, then your Q is going to be here, and then your secant line is going to be like this. If your h is like small enough, then you have this point 2 plus h is coming here, your Q is moved here, your secant line is very close to the tangent line. Okay, so what is delta y? Delta y is f of 2 plus h minus f of 2. 2 plus h is f of 2 plus h is 2 plus h squared, because our f is x squared, right? Minus f of 2. F of 2 is 2 squared is 4. So this is delta y. Over delta x is obviously h. Okay, this minus this is h. So we can simplify it actually. If you expanded it, you get 2 squared is 4. 2 times h is 2h times 2, 4h, plus h squared. Okay, 4 cancels with this 4, and I have what? I have 4h minus h squared left. 4h minus h squared left. But there is 4h minus h squared, I'm saying, right? Okay. And then I can simplify the h as well. Actually, plus 4h plus h squared. I'm sorry, 4h plus h squared. Since I cannot write, let me write it here. Writing is much better, okay? Let me write it here, because otherwise you may not follow. So we are talking about f 2 plus h, 2 plus, where's 2 plus? 2 plus h, sorry. Okay. F of 2 plus h, 2 plus h minus f of h. Okay, minus f of h. Okay, so this is what? This is equal, I'm going to just calculate this. 2 plus h is, we did that, it is 4h plus h squared, right? I mean, if you do the f of h is 4, so you get 4h plus h squared. Okay, let me make it bigger. And if you divide this by h, you're going to get 4 plus h. Okay, this is divided by, let me put this in square bracket. Let's divide this by what? H. Then you're going to get h plus 4, definitely. Okay? Okay, we got this from here. So this is the secant slope of the secant line, and as h gets close to 0, this is going to drop down to some number less than 4. I mean, pardon, h is positive, so it's going to be, as h gets close to 0, so this is going to be 4, gets close to 4. So the slope of the tangent line is actually 4, we can say. And in the future, we are going to be talking about the derivative of a function. You remember, what's the derivative of x squared? You remember from high school. Okay, the derivative of, we will see them later on, but I'm just telling you. Okay, what's the derivative of f of x? X squared is 2 times x, you will see. Okay, let's put the value at 2, and you're going to get 4 as the slope of the tangent line. Okay, let's plug in 2 here. And this is 2 times 2 is going to give you 4. And this is the slope of the tangent line. Slope of the tangent line. All right. So actually, that's what we found. So if h goes to 0, you get 4 as well. So they match. Okay. In other words, later on, we are going to see if you take the limit. Okay. Later on, we are going to see if you take the limit of this limit as h goes to 0. Okay. Limit of this as h goes to 0. We get that. Limit is 4. Okay, they are all related. Okay, so taking this limit actually is later on. Actually, we are going to define it. This we will define. Okay, next we will define in the next class. In the next class, we will define. Okay, this is okay as h goes to 0, of course. Okay, this thing is nothing but f prime. F prime at 2. Okay, that's the definition we will give in the future. That's our goal, actually. That's what we want to get to. So the derivative definition comes from this rate of change of average rate of change. Okay, it comes from that. Okay, see, this is average rate of change. This part, you just take the limit and you get the derivative. Okay, that's the goal we get to. Okay, that's how in the old times mathematicians come up with the derivative. Okay, and it all comes up from the slopes of the secant line, and that's it. Any questions about this? Is this clear?
Last part, I've derivative 2 limits.
Okay, it's not clear?
Yes.
Yeah, I know it's not clear, but this is a preparation for the future class. In our next class, actually, we are going to give the definition of the derivative. And then we are going to say, so far, we talked about this average rate of change. And why did we work on this? The reason we work on these things is that it's going to help us to give a definition of the derivative. Okay? And this last part which you said is the definition of the derivative. If you take the limit of the average rate of change as h goes to 0, by the way, then you get the derivative at 2, which means this is the let me write that this is the slope of the tangent line. Slope of the tangent line. You see, all of them are all related to each other. So slope of the tangent line is related to the slope of the secant lines, and slope of the tangent line is related to the average rate of change, and average rate of change is related to the derivative. Okay, you just take the limit of the average rate. So these things are one after another, they are related, and this is the final relationship we want to see. Okay, definition of the derivative in terms of limit of the average rate of change. Okay, so that's our goal to get to. Okay, I'm just telling you all now the whole picture ahead of time, so that you know why we are working on these things. So far we talked about secant line, don't forget about that. And then we talked about the average speed. Okay, remember the table we built. Okay, and remember average rate of change. Okay, which is the general name to average speed. And then remember taking the limit of such average rate of change to get to the slope of the tangent line. Okay, and then yeah, these type of things. And remember this picture. This picture also is very informative. Okay, so next things we are going to go through them next class, because we are done. So these things we are going to talk. See, we look at the future future lecture notes. We have tables again. These tables. Okay, we are going to see them in this section quite often. Okay, and then we are going to talk about the limits, the properties, and here's another table. Okay, this is we are trying to find some limits by building these tables. Okay, so then we have some theorems, sandwich theorem for the limits. Okay, we are going to talk about that. We are going to skip this precise definition of a limit. Section 2.3 we will skip. Okay, and then let's see what's in section 2.4. We are going to talk about the one-sided limits. Okay, nice examples here. And let's see, then we are going to talk about the continuity. All right, and then let's see what do we have next. Is this all? Let's see. Section 2.6 is about limits involving infinity, because after we define limits, we will look at what happens to infinite limits or involving infinity, asymptotes. We talked a little bit at the beginning of the class last week what asymptotes are. So we are going to go through it using the limits. Okay. And then horizontal asymptote, vertical asymptote, we will talk about. Almost done. I'm gonna let you go in 1 minute. I think that's it so far. Yeah. So that's what we are gonna cover in chapter 2. It's gonna go really fast, and you're gonna be okay. Do you have any questions? I think that's all I want to say today. Yeah, can you please upload chapter 1 and chapter 2 on the limit system? Yes, I can. I put it in here, Güchan. I uploaded to here. You can see it in the chat. You can copy it down from chat. Yes, I should upload them on LMS as well. I think I have a copy of chapter 1, but probably it's the old version, so I should upload that. Chapter 2, I'm going to put it on there, but see, after we finish chapter 2, the notes on there are going to be different, so you should always use the updated copy, okay? And that's it. Thank you for coming. If you don't have any questions, I can stop, but let me get the attendance sheet here. Download attendance. Yeah, I'm gonna download that. Don't leave before I do that, okay? Okay. All right, so this is gonna be section 3. This is the second hour. This is the second hour's attendance. Okay. Okay, thank you. That's all for me today, and if you have any questions, let me know. And other than that, I will just turn it off. Okay, there's a question here, conversation. Yeah, you say bye. You can say bye at the end, please. Yeah. Yes, Mohammed Fahmi, what's your question? Mohammed Fahmi, do you have a question? I can't see your question, by the way. Okay. Okay, I think it was an old note, right? I don't see a new one from you. Okay. Okay, bye-bye. Take care.